And we will be covering one of those, which is probably the most popular one today for distributed version control systems, which is Git or Git. We will be learning what it does, what we can do with it, and the very first steps into creating a repository, making a commit, the push, all that terminology we will be covering here. And I think for several use cases in research, in scientific research, it's important. It's something that could come useful. The second topic will be compiling codes. Not necessarily all of you will be doing this, but from time to time you receive a code, either because you was unfortunate enough to receive a code from the previous guy that just graduated, and you have to deal with that, and probably the PI have no idea how to compile that code. It will give it to you, okay, you need to work with this. So it's good for you to learn a little bit how you compile a code, the different libraries most commonly available, then how you deal with those, and the errors and the solutions that you can encounter when you are doing those things. And finally, I will introduce a couple of commands, a couple of packages that are useful when you are processing data, especially when you are post-processing data, and the code that you work, in whatever is your area of research, will produce a lot of output in text files, and you need to capture a certain amount of values, and it will be a pain to scroll across thousands, hundreds of thousands of lines of output just to capture one energy here, one pressure there, or something like that. So there are ways for efficiently capture that data. And that goes a little bit into shell scripting. So, well, what it does, even if eventually there are other kinds of scripting mechanisms today, like Python, some of those things you could do similarly with Python. But in particular, using the package that we will present today, grep and awk, AWK, and they are particularly powerful. And if you know how to use them, you can do these tasks much better than whatever you can do easily with Python. You can do it probably with Python, but it will need more coding, and you need better understanding of how to perform this kind of task efficiently. So we will be covering all that. For that, there are some materials, and I will be using some of that. So go here. I think it's you go here and here. So if you go to this URL that I will be pasting for you and on the chat, and you click on setup, right on the bottom, there is an instruction for downloading all the materials, the data and examples that we will be using today. So I will be also pasting this on the chat. Okay, so here I will be working on Open On Demand just because for me it's easier. I will be trying to use the terminal here, because otherwise I probably forget. At some point I will be using another terminal, and you will see what I'm sharing. It was not what I'm actually working, so I prefer to keep everything on the same browser. But whatever we will be presenting today works exactly the same if you just connect to the cluster directly via an SSH client, PuTTY, or you connect via your Mac or your Linux machine to the cluster, and you land on the head node. And for the most part, we will be working on the head node for the kind of things that we will be doing today. So let's start. So here, let's move into version control. So version control is a tool, is a package, is a software system solution that keeps tracks of changes of a folder, a collection of files, folders, such that you can eventually revert what you did, or allow several people, collaborators, to write on the same repository and keep track of the changes and contributions that other people do. There are, I mentioned, 3 typical scenarios for people like you who are doing research that involves computers and all that, where these kind of systems could come handy. One is if you are coding, if you are actually developing a code or improving another code, or making scripts, even if the scripts will run on a different code, whatever you are doing but involves some coding, this is a good tool. This is what originally was created for. So you keep track of the changes that you are doing to your code. If something was working and it's no longer working, so you got what you call a regression. So you can come back and review if doing something create a collateral damage somewhere else, which with complexity start bringing this kind of things. It happens in real life. This happens in even in the software. So you do something and you are creating a whole set of consequences that were unintended, and that allow you to trace those consequences and fix that properly. So that's the first use case. The second use case and the third use case, which they're kind of related, is that when you are writing a paper and you have collaborators and for that paper, so you have your text, especially if you are working in LaTeX, which most people, especially in engineering science, especially in basic science, use LaTeX for writing papers. So it's a text file with some figures attached, with some and the bibliography in BibTeX, so all that with proper formatting. So those are basically text files, except for the figures. So you would like to keep a track of those. Eventually, you are not the only, you could be the first name in the paper, but the paper is also reviewing or receiving some collaboration from somewhere else, which is another lab in another institution. So they will be contributing some paragraphs or some tables or the results of some experiments or something. So they can contribute those and put the figures, and all the team is working on a repository. And as you avoid having to send which is what the end many people do, is to start sending back emails. Okay, this is my contribution, this is my, and you send the email back to your professor, and the professor will make some corrections, and after you receive another email from the collaborators, but the corrections from them were still not implemented because you received those from different channels, and after you get a mess with the paragraphs coming correcting from your professor and changes coming from your collaborators in our institution, it will be a nightmare. So using a version control system is keep you sanity on all that. And the final is your thesis. In your thesis, you probably are the only one working on that. It's true, but this is a big effort in a narrative. So you have different chapters. Probably you have a text file for each chapter, and you have figures, and what happens in that case is that you send the manuscript to your professor. The professor will start making corrections, and you will be correcting some things. He will tell you that you need to change some figures, or you need to rerun scripts to recreate the figures because you need to take in account some extra feature or some extra, or you need to change some units or something. And so in that case, it's good to have that under a version control, to keep that out of your own computer in the eventuality that your computer breaks, you lost it or something. Your thesis is somewhere where you can recover it, and you keep track of the changes and the evolution of your manuscript. Those are three scenarios where this makes all sense, and you will be saving a lot of headaches and a lot of time if you learn to do this properly. By the way, we have, still is, I think it's true, we have the ability to create private repositories for you on GitHub, which is a service that by default, they offer free repositories, but those free repositories are public. So if you want to keep some of your work private, we can create a repository and in our organization for you and keep that repository private so you can work with it. And at that moment, you can decide who will be able to see your repository and contribute to that. So you keep some control on the access to that repository. So that's something that we can do. You just send us a message, and we can provide you with that facility. So let's review this a little bit in the text, and now after that I will be doing this a little bit in practice. So the idea is basically the following: everything that we are doing is command line interface. There are another software, and software if you are using Windows, Mac. I'm not sure Linux if they have it. For example, for GitHub, that allow you to do many of these kind of things just from a graphic user interface. So you can commit, you can push, you can pull. Very simple, very easy. As it's called GitHub Desktop. But what we will be doing is from the command line interface, and all the commands with this particular version control, which is called Git. The command starts with Git. That's everything starts with that. This is, by the way, not the only one. There is another one called Mercurial. There is the old version of this. The one of the first that emerged is SVN, subversion of. There are several, but this one is popular. Has many packages, scientific or not. They are in this kind of repositories, GitHub, GitLab, or something, and they are managed by this system. And this was created by the same people who create to manage the Linux kernel, by the way. So it was used for big projects with many people involved in a repository or something. So everything starts by creating a repo. And one way of creating a repository is executing this command. At that moment, you have your repo, your first repository in your computer. Another alternative is to create a repository on a machine on internet like GitHub. At that moment, you create there. You don't have to execute this command. You just make a clone and you start operating with the clone on your computer, and you operate with that. So you create create your repository, and all that happens is that you create a hidden folder .git that will contain all the internal machinery, some files that will control all that is happening to repository. That's the first command. Not often used because you just prefer to use something like GitLab or GitHub, and you just clone it from you create there and you clone it. And the second command that you use all the time is git status. With this command, you just see how the files that you are dealing with are compared what the knowledge of Git it has about the status of those files. If the file have changed, if some file has been removed, if there is something that you need to pull because there are changes in the parent repository, and eventually you want to bring those changes and integrate those to your copy, all that. So you execute this command git status all the time. There are more commands like git add. I will be showing that in practice to add files to the version control system. When you just put those files on the repo, they are not version control. You need to add those so the system recognizes those files for changes. Again, git status, the commit command option, the commit option is to accept or integrate those changes into like a milestone. You make a mark and you say, okay, these changes will receive, you wrap them with a commit. And the final commands, I think, are the push and pull, and probably at the bottom here. And I will probably mention those in practice. So when you want to, for example, send those changes to the parent repository and pulling those changes back to your repository. So this is better to learn it in practice. So you see here the text, you can come back and read it. That's what this text was created for. So for you to read. But let's do this in practice. Let's see, let's start with this. I will be, okay, I will be, let's see if I have. So by the way, if you take what I paste from the chat here, I will probably do it again. To access this is executing this command, git clone. It will fail, by the way, because, okay, I will remove mine and I will be cloning this again. So this is the command that you need to do. This, by the way, is cloning a repository. So, so this is the first command, just to grab the materials that we will be using today. So if you won't go here to workshops and introduction HPC, there is one, is 13 version control. Where you will see the files that I will be working in a minute for I think the second exercise. But the first thing that I will be doing is following the instructions with you, so you can reproduce this if you want. So the first is to create an empty repository. So that's what I will be doing. But in my case, I already have this. If this is the first time that you are using Git, for example, on the cluster, if you want to have a repository, which is another good thing to do, that if especially you are doing coding, that you have a machine where you can submit jobs and test things, and there you have the code. You could be working at home on your own computer with some stuff, and you use the cluster like a test bench for testing the performance of your code, or if your code is doing what it's supposed to be doing. So in that case, if this is the first time, you need to execute this just to declare to Git internally that all the changes that you are doing there, they belong to you. So you put your name and your email. The reason for that is that every time that you do a commit, this milestone, it will be kind of signed. It will receive your name and the email address such that you see who did that change. And several people contributed with that. So you can see who did that, when, and in that case, you can blame if something was wrong with that. So that's it. I already have it, so I will not execute in that command, but I will create in say paper one. I will be creating like a folder here. Imagine that I will be working on one paper here, and I will make this folder Git repository. So right now, if you see, there is nothing there. The first command that I will execute, by the way, there is something here. This I have by default, but I think that Git, a very current new version or relatively new version of Git on the system. Otherwise, I think most likely you don't have this. I don't think this is by default on the class. You need, or you would like to load this model. So why? Because the version of Git on the cluster that comes from Red Hat is very old. So let me show you that in practice. Module purge, and you try to see Git version is 1.8, and that could create conflicts. If you are using Git, GitHub or something, you are using a repository on those services. Sometimes this version is so old that it will break. It will create some inconsistencies, or simply the command will not run. So for that reason, it's always better to load a newer version, and this is relatively new. So that is what I always do by default, but on my account. So this is something that you can keep it like this. And at that moment, if you execute again, the version that you are using is 2.29. The fact is, if you are using something like a version like this, 2.29, 2.24 or something, it's good enough. It's as soon as you passes the version 2 is good. So that's the first thing. So I'm using Git version 2, and I will be creating, following here the instructions. I will be initializing this folder as a under version control. So Git init. So it will say, okay, this folder, paper one, is now under version control. It has nothing, but now if you see this, there is a new .git folder. So this is an indication that this folder here is under version control, and the package or the software that we are using for version control is Git. If you are using SVN, you will see something like this, that the folder is SVN. I think Bazaar was something that they used like 10 years ago or 12 years ago. I don't think that it still anymore. It doesn't exist anymore. I think it was go out of usage and people would move to some other solutions. At that moment, it was .bcr, and Mercurial has something similar to that. So different solutions will do pretty much the same thing. We'll create a folder, a hidden folder, hidden because it starts with a dot. So if you execute it this way, you will see nothing. It's not hidden for any kind of security reason. It's because under normal circumstances, you don't want to see it and you don't care that it's there. So that is the first thing. So you create you initialize a folder like an empty repository. that's the first exercise here. You can see, well, the Git status, which is telling you that no commits, everything is fine, you have nothing, so that is all right. So now I will be adding a structure to the repository. For that, I am creating, adding a few files and folders, which is a structure that I follow on papers. And for me, it makes sense. It's like a good idea. Well, to have like a data, scripts, paper, plots. So the scripts are basically Python scripts, for example, that will recreate some figures, some plot based on the data that has been kind of very narrowly selected. So those the tables that I need to recreate a certain plot. If I need to do more simulation, the simulation will happen somewhere else, and the tables will finish in the data folder. The plots, so the figures that will go in the paper, I will put them in plots, and the paper itself, which is one or more text files, they will be here. And after, I need to add at least some empty file just for the folder to exist on Git. So Git will not track empty folders by default. So that's why I'm just faking a few README files or something there. So that's pretty much what I will be doing here in the next few minutes. So data, for example, paper, and plots and scripts. Data, paper, plots, scripts, and I will be touching. So this is creating. We will be using all that we learned before. This is like you can create a README. Modern version of that is create a markdown README. So I will pretty much creating those empty folders, paper, scripts, and plots. Okay, all those are empty files, and touch is a way of creating files, empty files, or changing the timestamp for a file if the file already exists. So now let's see what happened when I execute Git status. I will tell me, oh, okay, so there are some untracked files, and if you want those files to be on the version control system, you need to add them. You need to say, okay, explicitly, I would like to add the data folder to the repository. Otherwise, they will remain untracked, but they will be visible here when you execute Git status. So if you execute Git status again, you will see that now Git recognizes that there is a new file that has been added to the repository. So this file will be under version control. It will track changes of this file. Let me see what I was suggesting. So I was suggesting to execute, well, all that. This is another way of doing it. I will be doing that here. So with this, I will be adding all 4 folders to the version control. And I will be creating my first commit. This is another often used command. So the way you proceed with Git is you work with your text, with your files, you add plots, you put figures, you put scripts, you populate that, you add the folder or add individual files. It will be up to you. If you add the folder, it will be adding recursively everything inside that folder, or you add specific files. That's another thing. That's the first thing that you do. Second thing that you do is make a commit. This is making this wrapping. I would call it like a wrapping, putting that and creating like, okay, this is a post, something that I will be doing. And usually you can put it like a small message. If you don't put this, a message, it will open your default editor, something that eventually you can change. But by default, I think will be VI probably, or Nano. I'm not sure what is the default on the system. And at that moment, you will have to type a description of the changes, which is another good procedure. So describe what you did on that on that commit. What changes you introduce? Are you fixing typos? Are you improving something? Is because you developed something else? Is because I want correcting chapter this, chapter that, or I will be fixing something that was an error on the energy, or the units were wrong here. So this change is correcting that. So every commit should be followed by a description of what you did there. And you should not be afraid of making commits very, very often. So that is something that is encouraged in this kind of thing, to do commits often and keep incremental steps, instead of working for a week on something and after having what we call a touch bump, a bunch of changes that after that you don't know even what you did with all that. So now that is all those changes, and now I am suggesting you to clone again the repository with all this. And I have one example when I am populating all this. So I will be, I think this is, I will be copying all the material here, and I will show you how you can copy all that to my paper one. Workshops, so introduction HPC, and I think it's 13 version control. So here I have this project, and this project is pretty much having all that. So I will be making a rsync of the project like this, and the slash at the end matters. This is important. And I will be copying that to my paper one. So it will be making a copy of that, populating all that. Imagine that I would develop the repository now. So you see that I have the folders, but now they have more stuff. So they have some data, some a paper, and the LaTeX, the file there, and also the PDF that you generate when you compile the paper. You produce the paper with the equations, all that. Here, the plots that I will produce with the scripts, and some scripts that I have here that will generate some plots, some figures, on all that. By default, we don't have LaTeX here, and that's not the purpose. This is not a workshop on LaTeX. I will be just showing you for curiosity, which is the main paper. It's nothing. It's a very small file. It's a text file. This is a LaTeX document for the paper. So here I am just using one figure, which is, what is the figure here? Is this figure, include graphics, this figure here, which is a PDF. And I will probably, well, no, I don't even have an equation here. So this is very, very minimal then. So git status, I will say, okay, many things change here. So my README has been modified. The files that I have here, the paper, there are a lot of new files here that I was not aware of. Okay, so if I want, I need to make a commit of this, and I think that that's what we'll be doing. Okay. Yep. Here I forgot this is done out big captures. There is a Dutch M here that I forgot, so I need to correct that. So I will be git add. There is another way. If you want to accept all those changes, you can just put git add dot. At that moment, you have git status and you have all those changes integrated into the repository, and you can just git commit -m and populate the paper. So I have another command is git log, for example, and it will show you all those commits, so all those steps, and you can come back and revert and change and see a different version and return. There are a few commands, but this time the workshop is shorter, so I don't have time to get into that. I think that the next thing that I will be doing is adding a few extra things to the papers, to the document here, compiling it. For that, you will need LaTeX. So there are ways you can access LaTeX on. We have some Singularity containers with LaTeX in case that you need to compile something. And so here you will be following more procedures for that, for changing that. Eventually for reverting, I don't know if I include that. And the final things that you do here, okay, this is another exercise for another repository where I have code. So this is for a paper I have in this exercise this is for a code that is actually doing some calculations, and this is under version control. It's also have a builder with makes and all that. So that is doing, and a few extra commands here for pushing and pulling, especially when you are working with remote. You have a remote repository, for example, in GitHub or GitLab, and you want to pull. So pushing is bringing the changes, the commits back to your computer, back to your repository, and pull is bringing those down. Push is sending those back to the remote repository. And a few links to some other stuff that you can do with Git. So unfortunately, now that the workshops are a little bit more compressed, I have less time to go into those details. But the document is there, you can follow, and there are very, very nice. I collect a few tutorials that are really, really good. You can follow step by step. They have been very mature, and they guide you into all those commands, checkouts, how you revert, how you remove one file from the all that is well reversed, especially these Atlassian Git tutorials that are really, really good. But now we have to move to some other stuff that also demands some time. So let's keep it like this. This is one thing. So now compiling code. I will be demonstrating here. Let me see. For this, I will be going workshop and so on, and I will be going to introduction HPC. I don't think it's 14. So here, if you clone the repository, here I have all the examples and even more that I will be covering today. And I will try to compile also a code, complete code that I pick up. So just for you to know how you compile a code, let's say a big one, and I will demonstrate very explicitly with small ones, how is the compilation of all that. So the first thing is, for example, a code that uses parallelization. So an OpenMP parallelization. So it is called example of OMP. So let's see how that works. So is here. Let's go over the pip.c. So it's this code. It's very small. How you know that this uses OpenMP? Well, there are several things. One is that this in the header here for OpenMP. Not all codes that uses OpenMP include a header. But more importantly, they have a pragma here. This pragma. This code, you can compile it without OpenMP. It will work. No, it will not work because they had the header. But if and the reason for the header it was why I was using the header here. Not really sure. Oh yeah, because I was using this function. Okay, so this code mandatorily needs to be compiled with OpenMP. So now let's review what it does. How do you compile that? So by default, module purge. By default, you have the only compiler that you have available. If you don't have any module loaded on the system, the only compiler that you have is GCC. And the version of GCC is 4.8 on a Red Hat 7, which is old. This is old, very old. It works. It works. The reason why I say is old is because several things. OpenMP, the OpenMP supported at that time for today's standard is very old. So there are new features that have been integrated that people often use in code that GCC 4.8 doesn't support. That's one thing. And also it doesn't support certain extension instructions that increase the performance of a code. And they are in this kind of newer processors. Let's say starting with 2-3 generations ago. So Haswell, IV, Haswell, Broadwell, and those here, all those include some extra extensions called AVX. So what they basically do is that they take numbers, 2 numbers, and they stick those numbers together. And in one CPU cycle, they are capable of doing operations with multiple numbers at the same time. So they pretty much, in principle, double. They are doing multiple operations in one cycle. So that is kind of a very, very low level parallelism that is integrated in those newer processors. And you would like, especially for scientific code, to take advantage of that. So GCC 4.8 will not offer anything of that. So that's why you typically will not use it. But let's imagine that you will like to compile it. Well, I think that for this small thing, it will probably work. The first thing that you would like to try to do is, okay, let's see if that a simple compilation would work. This will fail. And it will fail because it doesn't understand this and this. Has no idea what it is. And the reason for that is because it was not integrated with OpenMP and the header was there. So you need to add this extra flag to add OpenMP there. And at that moment, you can compile it. That's one thing. If you want to know all this, there is the manual page for GCC, and you can search for OpenMP with a slash. By the way, you're not familiar with this way of like VI searching. To search on a man page is in a slash. You hit a slash and you type OpenMP, for example, and you see here the -F OpenMP. And to search further into the manual, those manuals are thousands of lines. So you just hit N and it will tell you, okay, with -F OpenMP, It will enabling handling of OpenMP directives. It will also integrate the header OpenMP, so you will be able to use parallelization, the OpenMP parallelization, so using multiple cores on one machine for one process in the system. So that is exactly what I did here. And at that moment, you can execute this code, and this code is launching as many threads as cores it think it has. So, and the head node has 48 threads because hyperthreading has been enabled on this machine, but the actual number of CPU cores is 24. So it has 24 cores, enabling up hyperthreading. You double the figure, you have 48. So OpenMP thinks that it can launch 48 threads, and you can take advantage of those 48 threads. So they will be launching those, and they will operate, those threads will execute in parallel. They will execute concurrently the operation, which is just printing a line on the system. So a number of threads will be 48. And each thread was printed independently by different cores. Eventually, the same core at the end was taking care of 2 threads in average. And they will print this. So that is the first thing that how you print the code that uses OpenMP. And after, okay, I have something for those who are interested in knowing this. Is something that we use often, is limiting the number of threads, and this is the way of declaring at the runtime. So the code was already compiled. The code is taking parallelization, but it's using an arbitrary number of threads. You decide at runtime how many. By default is the number of cores, real or virtual, that the operating system sees. With this, you limit, with this variable here, you limit the number of threads that you are creating, and that you are allowing the code to see, to use. So that is one thing. Okay, that is one code. Second one is this, an MPI code. So this is a little bit more complex. There is, I think, I think this it should be example MPI or something. Yeah, I think it's this one, example MPI. Again, a very small code. The point here is not to learn programming. So I pick small codes. I will not dig into the code, the actual structure of parallel programming at all. How you know that this code uses MPI? Well, first the header is there. So this is called a header in C, include. So it includes the functionality for MPI, for message passing interface, that allow this code eventually to use multiple machines working on the same problem. So multiple compute nodes, multiple machines working together on a single problem. And all MPI codes at some point, before anything else happens MPI related, they have an MPI init. And all MPI codes, at some point, if they are correctly written, they will have an MPI finalize. So with this and all those MPI underscore something, you know for sure that this code uses MPI. So let's go into this, how we compile this code. So here, right now, we don't have any modules, and we don't have anything here to compile an MPI code. We have here module available and the lang, several compilers, And also, if you see here, yeah, in the Intel section, we have also MPI implementations. So compilers, this one will disappear in a few days. So 11, I will remove it. So effectively, you have two versions of GCC, several Intel compilers, and here we have more compilers here. More versions, more compilers here. So you have, let's consider this one here. This is the GCC compiler version 12, and you have the NVIDIA compilers. So it's right here. And if you load this module, NVIDIA compilers also include MPI. So this one is just a compiler. This one includes MPI. So we can use this one if you like. And here, the Intel also has MPI, and they also have here a compiler, the Intel compilers. But let's use the NVIDIA compilers. This is just one. I will just pick this one, module load, lang, module load, NVIDIA H. You can keep it like this, and it will load the latest version, which is the 23.3. So that's the latest version. Oh, that's the latest version at the time when I installed this. So it's very recent, from 2022. So now, how you know that you have an MPI compiler or an MPI, you can compile codes with MPI, is because you have this this executable here. Give me a second. So this is the NVIDIA compiler. And what the people at NVIDIA did was they took, I think it's OpenMP, if I'm not wrong. Yeah, they put OpenMP in. So this is OpenMPI. So one implementation of MPI that NVIDIA took and they integrate with their own compilers. So the compilers for NVIDIA are this is the C compiler from NVIDIA that used to be the PGI, the Portland Group compilers. So they bought that company, they integrated, and a few years ago they just rebranded, and now they are called the NVIDIA compilers, or the NVIDIA HPC suite. So they have the three major languages in scientific computing. Real scientific computing, there are basically three languages, period. It's C, C++, Fortran, no particular order. Fortran, C, C++. Those are the languages for most of the, let's say, real computational intensive scientific software is created, period. Okay, so we will be using this. We will compile this example with this compile. What this is doing, MPICC, is just what we call a wrapper. It's a script, actually. It's a script that is preparing the actual compiler to receive MPI code. So we will integrate the headers. We'll do some changes. Let's call it that way. We'll add some extra layers so the code can compile with MPI and prepare it correctly. You know that you compile correctly when you see nothing here. That's a good thing. And you can test this, for example, for processors. By default, if you want to compile the code, and just for quick compilation, it will always generate a file called a.out. So that's what you do when you execute here. So that, and I will show you in a minute. So by default, when you compile, it will generate an executable binary, an executable a.out. And for me, being lazy, and that's what I'm doing because I'm demonstrating this quickly, but I will show in a minute what you do with it. So it will have some messages as coded, trying to search for CUDA. It was created also for CUDA things, so I will put some extra messages, but it's actually working. So if you ignore all that, it's actually doing what the code's supposed to be doing. It's creating four processes, and each one of them will execute a line, and those could be on different machines, and eventually for bigger stuff, they will communicate to each other. So they will send like a big array or a big portion of information, and they will receive from other information. And for example, when you are computing a huge, imagine that you are computing something happening on the surface of the United States. So they will divide the map, they divide the whole surface for different processors, and they will have to share information about the boundaries of that division, of that what is called a domain decomposition. So each processor will have to transfer information about what is happening the boundary from the neighbors, so they can process the information from their own portion of the area. But that's how you compile a code that uses MPI. By the way, if you want to change the name of the executable, it's usually with this -o. So example, you can put something more meaningful like this, and at that moment, the executable will receive that name. Okay. So that is MPI. In that case, I was using something else. I was using GCC here, and one of the parallel implementations that I have here, module available in parallel. So there are several implementations of MPI. OpenMPI is one of them. There is another called MPI, MVA pitch, and MPitch. So those are different implementations. There are advantages and disadvantages of them. And the Intel implementation of MPI is basically a slightly modified version of this one, of MPitch. So that's MPI. And here is a description of the different ways of compiling this with other implementations. So if you want, you can clean this. Let me see. I probably can't time for showing. Module. If you want to use compiler, which is the Intel compiler, and MPI. Let me see if this works. There is this MPI CC example. MPI. Let me see if this works. No. There is something happening here. This one's yes. There is something broken with ICC. With the newest version doesn't support library. So you need to. This one here is using Intel implementation of MPI, but on top of the GCC compilers. So all that is described here. So what are you using depending on if you are using the Intel compilers or the GCC compilers? The command changes a little bit. So now let's change gears into something else, libraries. So you are compiling something that uses some libraries. And one of those libraries, most popular, I think the widely spread library that many scientific codes use one way or another is BLAS and LAPACK. BLAS, I think it stands for Basic Linear Algebra Subroutines. I think it's the name of that. And LAPAC also stands for something that I don't remember exactly. Linear algebra and something. So those are two packages that has been written, I think, 40 years ago. They were written in Fortran 77, probably not even that. So they were written back in the 70s. They are meant to execute linear algebra. And linear algebra, in the case of BLAS, is something like vector-vector multiplications, matrix vector multiplications, matrix vector times a constant plus a vector. That sort of generic templates. So those are like prototypical operations that you use all the time in many domains, in many circumstances. You are doing that linear algebra stuff. That is BLAS. And LAPAC are more elaborated linear algebra things, like taking a matrix and decomposing that in multiple matrices, that shows that when you multiply all those matrices, you reconstruct the original one, and those matrices have some interesting properties. So it could be a triangular, upper triangular, lower triangular. You can take a matrix and decompose that, and take the eigenvectors, eigenvalues of them of the matrix, inverting the matrix. So numerically, all that numerical operations on matrices is LAPAC. So I have one case here that uses LAPAC. Let me capture it. This is Fortran. So I will probably see it here. What is the name? It's, let me see if I can capture it. I think it's this one. Yes, so it's better here on VI because it puts some coloring. So here, this is one of those typical cases of a BLAS subroutine. This is Fortran, by the way. This is small Fortran 90, Fortran 2003 kind of code. So this one is a double precision. That's what the name is. A double precision general. This is, I think, it's vector matrix multiplication. I need to check exactly what it is. Let me see if I got exactly what it is. Yes, it's a matrix vector, because so you have A here, this is a matrix here, and this is a vector. So it's doing the matrix vector multiplication. So that is what we would like to compile. So if you try let's go back here, module purge, and let's try with a different compiler. Just blank GCC 12. Okay, this one. This compiler. So you try to compile with gfortran, which is the Fortran compiler in the GNU compiler collection. It will fail. It will fail because it doesn't know what to do with this. Well, with the random seed, first thing, doesn't know what to do with that, and it doesn't know what to do with this operation here. So that is the first thing. So the random seed is another code that is right there. So this is another Fortran code. So now we have the functionality of this code is split into Fortran codes. This one here that we need to compile first, and this one is just a subroutine, so it's not capable of running on its own because it's not a program in Fortran. So we need to compile this, and after we need to use the output file, the output code generated from that, to compile the next one. So that is exactly what I'm doing here. So I compile that one, and after I can compile this one. And for this one, there are several implementations of BLAS and LAPACK. I suggest you to avoid as much as possible this module. Let me see. I don't think that I have this. I suggest try not to use the original LAPACK and BLAS. I don't think that I have here the red BLAS. Don't try to use those. This is just if you really need to test something with the reference BLAS, so the almost the original code, the original codes, the original subroutines. The reason for that is that there are better options. One of those options is this one, for example, this one here, OpenBLAS. The difference between OpenBLAS and the reference BLAS is the OpenBLAS has been compiled, it has been developed with multi-threading. It means that if you have a big matrix or a big vector, it's capable of cutting that in pieces and do all those matrix multiplications with the different pieces with different cores. And the machines that we have that we have on Thorny, they have 40 cores. So if you have a huge matrix, you can get a big advantage on using something that is uses multi-threading compared with the reference BLAS that is serial, is just using one core. So try not to use this one if it's possible. And for you, always prefer the OpenBLAS. And we have an OpenBLAS compiled specifically for the GCC 12.2. So that is what I will be loading here. Module load this one. So if you see now my modules, I have the GCC and I have OpenBLAS available there. And now I will be compiling this. So I will be compiling the Fortran code, the file that I generate here when I compile this, which is this object file, and then I am adding this, and this is searching for the library for OpenBLAS, and it will integrate that and knows what this routine offers. So if you do not try to compile that, it will tell you, okay, this is not known, and this is one of the BLAS libraries. So OpenBLAS has the BLAS and LAPACK integrated. So it has that name, but it's also including the LAPACK stuff. So with this, you compile it and you can execute it. Okay, so you have the vector. It's generated, I think, random vectors, and it's on a random matrix, and is computing the multiplication, I think, if I'm not wrong, but that's when I go. Okay, so let's move on. More stuff here. Well, let me see. We have HD5. We have 50. Okay, I would like to probably this one is worded, and I would like after in the final 5 minutes to demonstrate how you compile a complete code, a code that you download over internet, how you compile it. So let's take this example. It is also illustrative of some other stuff. So HDF5, this is a library that provide you to a very robust open source way of storing large amounts of numerical data, special numerical data, in a binary form. If you don't know this library, you could feel tempted to store your data in just a text file, just numbers, the columns of numbers. That's what beginners do. We all do when you are exporting the tables, numbers, energies, pressure, temperature, whatever that we need to print, or positions of atoms, whatever. We just print this in text file. This is a terrible idea. It's easy. It's very easy. You print F and you print whatever you want. And the reason why it's a terrible idea is if you print many of those, it's a text file. Every single time that you read that, if you use a computer to read all that, the computer has to read every single character and reconstruct the floating point number, the number, back into the internal representation for the computer on that of that number. It will take a nanosecond. It will take a few nanoseconds or something like that. But if you have millions, hundreds of millions of numbers, well, it will take seconds, or will take far more time to do that. So it's inefficient. And if you do that repetitively, you have many of those files. You don't want that. The second reason is that text files consume far more space than storing that in a binary form. So that's why you want to store that data preferentially on a binary form. So you could feel tempted to store, and you can do it, for example, in Fortran, to store all those numbers in a binary format directly. But now you have another problem, is that different computers have different representations for numbers. And now if you are doing that and you take that data and use a different computer and a different architecture, the number there is represented differently. So when you read the file, either you have to translate by hand all those bits, you have to change the ordering of the bits every single time that you are reading the number, or you just need, you read garbage. The computer will not make sense of what it's reading, simply because it was written on a different architecture. So HDF is solving all that. And also there are limitations of storing metadata. So the data that is telling you about the data that you have, so what it represents, what is the meaning of the different columns, all that, units, for example, all that is hard to integrate. You can put it on the text message or something that is not standard, or something, all that. HDF5 is one solution that is open source that can kind of cover you in all those aspects. Storing the file in a binary format is very efficient. It's portable. You can move it into different architectures, and you can have an hierarchy of data with it. So that's what we'll be using here. I will be this probably have changed, but I will be using something else. I will see what we have here. So the code is, I think it's this one. Is this code? So then this code is written in C. It's using HDF5, and it's basically let me see. It's creating what in that library is called a data set. Here, it's adding like the dimensions of a matrix that I will be storing, and I will be adding that, and after I will be creating a file that will contain the information of that. So that, and after that is closing the file, and that's it. So it's a very minimal thing to write data, and that the purpose here is to compile this code, somehow compile the code. So module, let me see which modules I have here. Well, I will try to use this. So what I have available here is here in list. Available in lips. Well, so here, so there is around here those HDF5, and what I would like to use is this one. I'm not concerned about MPI. There's another thing that this library has, is that it offers you, for those who are programming in MPI, so you can be running on multiple computers. HDF5 also offers parallel I/O. That means that different processes can be writing and reading on the same file simultaneously, and the system will take care of consistency on self-consistency of the file. So otherwise, if you try to do this naively, what happens, it will be just writing a file and will be destroying the changes that another process that enters and take the file and start making also changes at the same time. So it will have some mechanisms to protect the file and build a consistent file when multiple processors are reading and writing on the document. But we are not concerned with that, so we will be loading this module load this library here. Okay, so right now what I have is all this. I don't care about OpenBlast in this case, but we have GCC and we have HDF5 library. And the way of compiling this, well, if you try to do it this way, you will get some errors like this, very similar to those. And the way of compiling properly here, there are two ways. One is explicitly using GCC and the C code. And if you want the output to be on a certain file, I show you that the O.dat or -O, and using this HDF -L for a library HDF5, and it will search for a certain file in the libraries, and it will compile this. And if you execute this, you will see another file here. That is this one. So this is a binary file. So if you try to see this file, let me see. What happens each time? So if you try to see this file and try to make sense of this file, well, it's just a binary file. This is you see by the way, this is a way of looking into a binary file. Otherwise, it will corrupt my entire terminal. You see, there is no way for you to make sense of the content of this. There are no characters except for a few letters there. There is no way of making sense of this. And there is one utility that allow you to see the content of this as a human. It's h5dump, and it's basically showing you the content of the file, the structure, and the metadata and the tables from something that a human can see. But the way you access this file is either using the library or using, for example, a Python package. There is a Python package for HDF5 that allow you to write and do all this at a high level from Python. So that H5py. So there's also alternatives to do this. So this is one way. I will probably skip the FFTW3. It's very similar. You have to load the library and compile it. But I would like to do now in a few minutes before I move to the shell scripting, one small example of what you do with the code, and it's this one. This is a different area. This is for bioinformatics. I don't know how many of you are in bioinformatics. So if you are in genomics or all this is something that you at some point you will be using. And so all of you using something like this or directly this for searching for similarities in genomes. And I will be downloading this code. So you see here, if you here, they give you a list of executables for that. So you see an RPM. This is a binary that you cannot use because you don't have control on the central software on the cluster. So you cannot use this. And there are versions for Mac OS, for Windows that have been pre-compiled. But I will be using the sources. So I will be compiling this code. And I will show you how to compile this code. So here, I can use this. So one way to download data for one file over internet is to copy the link that's what I did here. Copy the link of this file here. I copy the link and I move here, and I will be using wget to download. So that's the first thing. I download the code. And the next thing that I will be doing is to uncompress this code and CBI. So I will uncompress. It's a big code, so I will just start demonstrating how you compile this code. And this code is it's relatively simple, but they give me a few things that allow me to show you why modules are important, why you have this, how you cannot simply rely on compiling the code. Let me see. Let me try to do something like this. Module list. So I will be copying this because I will recreating this in a minute. Module purge. So right now I removed my modules, so I'm going back to GCC 4.8. Okay, and I would like to compile this and see I download the code and I would like to compile it. This is something that I will use, for example, in some cleaning some material or making some comparison with some reference, or something like that. The first thing is to try to compile that. This kind of codes, there are two major ways of this is a little bit atypical. They have an extra folder there, but usually they offer you something like a configure file. So that means that you are expected to execute this configure file, eventually with some extra arguments, to prepare the code for compilation. So the developers know that there are many different architectures, and people could can try to compile this on a machine with Intel or a machine with ARM, those newer processors that are, for example, on the newest Macs, or those tablets that they have lightweight processors that they work differently, or processors existing in other supercomputers that are not the traditional Intel or AMD processors, so x86. So this kind of scripts accommodate all the different, or try to accommodate the different architectures, different options, trying to search for which are the flags that you need to put in the compiler so this code can be compiled. And it's also doing some checks. And that is exactly what I would like to do. First, I will try to use it to see how far I can go. And you execute configure. And you see it right after a few seconds, you hit a wall here, and it says, okay, I cannot compile it because this particular code uses some features from C++ 17. And the GCC, I think the GCC here is from 2013, I think. Well, they put 2015 here. So at that time, the specification for GCC, for the language, 70, well, don't even exist at that time. And even if we were in the compiler were from 17, not necessarily everything that the specification for C++ 17 described was implemented right away. It takes a few years until all that implementation comes into fruition. So we need to change the compiler. We need to put a newer compiler somehow. Otherwise, we will not be able to compile this code. So that's why I will be going back. And I forgot to, let me see, I have to recover my okay, this one eventually is and I will reload this, some of those, and see the effect. Okay, so module list. So now I have the tree, and I can now configure this code. And it will check C++ 17, and now it's okay. You see, while it's checking the compiler, and now it's okay. Now it's also searching for some other libraries. It will probably detect that I have open blast there, so we will use it. I'm not super sure that it uses HDF5, but it will tell me at the end what it will be using. Also checks the processor, well, it checks what things can be done or not with this to compile this code successfully on this machine. And it will give me at the end like a summary. It's preparing all the make files, all some like extra files that are used during compilation, and you get something like this. So you get all this message here that says, okay, with using this, it enable OpenMP here. So this code can use multi-threading. That's another thing. What else? There are a few things that this code is not including. Some graphic user interface or OpenGL. So I don't know why it's using this. So Boost, which is a library for C++, I can insert that library, can offer that library if I feel I need it. It's taking HDF5. So it found HDF5, and now it's in the enable section. So now it's there. Also PNG, TIFF. So it detects some. It didn't detect Python 3. So it's using the Python that is in the system, which is Python 2. So it picks some things. It will tell you what it will be compiling. And now you are ready to compile. The compilation takes a few minutes. So I will just start compiling that. I will move to the final 30 minutes of this with this shell scripting, which is more important. But I will just let this compile. So there are some extra things that we can do during compilation is to do the compilation of the code, which is hundreds of source code, source files in C++. We can do it in parallel. And for that, make is capable of doing that. It detects like a tree of solutions, tree of files that can be compiled concurrently, and will now launch all those executions. Will compile the codes, multiple sources at the same time. I will not oversaturate the cluster because I don't know how many of you are following me and trying to do the same. And the machine has effectively 24 cores. So I will be just asking for 6. It will go slow and we will move to something else. Otherwise, it will be just using one, and it will compile one source after another, and it will probably take 30 minutes or 40 minutes to compile that. I don't know. So this is how you will start compiling the code with make-j, and you decide the number of threads for a make to compile in parallel. Let's move to something else. It will take some time to compile this code, and at the end you will get something like this. So you get, well, and there is something that I need to change. I need to fix this. You will see in a minute that we need to decide. Okay, but let's move on into the shell scripting. We have 30 minutes for this. You are more probably familiar with doing a scripting or doing this kind of things like post-processing in high-level languages. So when I refer to high-level languages, I probably mean either you're using Python, or you are using R, or you are using eventually Julia, And if you are in bioinformatics and you are from the old school, maybe you deal with Perl. Those are high-level languages where writing the code is relatively simple compared with low-level languages such as C, C++, Fortran, where you have to declare variables, that the variables need to be of the very specific type, and you have to type far more things to get the job done. On the contrary, on Python is very simple. You don't have to declare a specific type, data type for a variable, and it will work for whatever you put there for a variable. There is another alternative, which is shell scripting. Is the terminal that's in front of you when you are here, or we'll create a new one here. So this terminal here is also a programming language. This, what is interpreting your commands, is also capable of interpreting the logic of a program with loops, with conditionals, with all the typical stuff of a programming language. And that is called a shell. And programming the shell, so making this terminal, making the shell able to execute the workflow of a program, is called shell programming. With this, the idea is to achieve some automatization, eventually write more complex submission scripts that can take decisions based on an execution of something. And if the output works, for example, correct, it will do some extra thing, otherwise it will do something else. So that more complex execution is only possible if you are starting adding some scripting to your submission script or the codes that will process your data. So here I have one example of a shell script, a very minimal shell script. Okay, and this is here in my folder here. Production HPC, I think it's 15. Okay. And I have here tiny little scripts showing you what it does. So this one has no extension, nothing. If you want this, which is a 3 echo that we saw in the first, session, one of the 10 commands for Linux for you to learn is echo, which prints something on the screen, and you can use the shell with this example one to execute this under shell, and it will execute this. You see effectively printing the variables and the name of the machine and the current date. So it's also executing some extra commands and taking those and printing those on your screen. This is one, and this is the generic shell. This is whatever is the default shell in the system. There is one that is very popular. It's called Bash. So when you search over internet, you probably see Bash scripting, and they call Bash scripting. And this is just a particular case of a shell scripting that is very popular. So many people use that Bash, but it will produce exactly the same. For this very simple example, it's pretty much the same. So that's one way of writing a script where you have to explicitly put it to call the interpreter, the shell interpreter, in front of it, so it executes. Then the next thing that you can do is to add what is called a shebang. It's right here. It should be the very first line on your script that will indicate under which interpreter this shell script will run. And in this case, it will be the default SH. And at that moment, and if you do something like this, you change the permissions for that file, here, you will see here in the list of permissions that has an X. That X means it is executable. So you can execute this. And at that moment, you can execute this like this. So you don't have to put bash in front of it. You just call it directly. And you have to put this dot slash explicitly, because otherwise it will try to search for a command, example.2.sh, across your path. And the path, this location, this folder is not in this list of folders. So example2sh will not be there. And that's what I will. Yeah, I don't think anything. It will say, okay, it will go across all locations. It will not find the commands. It will say, okay, sorry, but I couldn't find that command in there. If you put it explicitly, you say, okay, I would like to execute this. That is right here. That is my second example. There are several interpreters for scripts. So I mentioned here that this one is what I'm using. Bash is another. Perl is a popular language, was a very popular language like 10, 20 years ago. Very, very good for processing strings. And they have, you can twist strings in very, very convoluted way with Perl. At some point, very hard to follow, but it was very, very popular. TCL is another language, and you join it with TK. It's a way of creating, for example, windows with the scripts. You can create windows with buttons and things like that. It's a nice scripting with some graphic user interface attached to it. And we will be using a little bit of Z, which is another interpreter for editing files, for changing text somehow. AWK, we will use that for processing. That's a big part of what we will be doing in this 20 minutes that we have left. And Python. And if you have the old Python, it will be something like this. If you are dealing with Python 3, your Python script should look like this. Usually be env, so it's searching for the location of Python 3, and it will use Python 3, assuming that everything is below inside that file is Python 3. It's a Python 3 script, and that's it. So let's go relatively fast and executing the examples, commenting a little bit. Comments all start with sharp. That's why submission scripts all start with sharp as batch, because that sharp will make that portion, that line, ignored by the shell scripting. It will be captured by S batch for the submission of the script. So that's how you make comments. If you need extra characters that are invisible, like new lines, tabulators, all that, there is this character slash followed by a letter, will add some characters that you cannot type on your keyboard. There are invisible characters, like a new line, how to express that you want to jump a new line or something. And also, if you put it at the end of one line, it means that whatever you're doing goes into the next line, so you can continue typing there, and it will, the echo will do that. So there is one example where I see this is example 4. That is, let me see, but I have an example 3 that I never executed. Okay, the difference, I probably jumped this. The difference between this and this. If you put double quotes, it will interpret the variable here with this double quotes. If you put single quotes, it will take the text as it is. It will not interpret variables that you put in single quotes. Different, for example, from Python, where single quotes and double quotes are on the same level, and you can use either to represent the order inside your string. So in shell, there is a difference between a single quote and a double quote. That's example 3. Example 4, it will show you a variety of ways. So you can put, for example, those escape characters and put extra lines and making vertical spaces. All that is described here. So you can follow here and compare what is there and what it produces. So here, this is the single quote and double quoting. Wildcards. So this is like a very crude, very simple way of replacing characters that could be arbitrary. So you are searching for, let's say, example, everything that starts with exam, whatever it is, you can put a star. It will be replacing that with everything. If you put like this, so let's well, why is not repeating this? So this one should replace one character only. I don't know what is not. Okay, so let's move on. Okay, redirections. So you can have something like this here. Let's say the tree that typically prints something on the screen. If you want to redirect that into a file, you can put the name of the file and it will redirect that into that file. If you put it twice, it will be appending to at the end of the file, it will add in more of the output of this will go at the end of this file. So this is a way of populating a file. So it will print multiple copies of all that. So that is the redirection, logical operators, and this is the and this is the or. I'm not sure if I have one example here for that. Let me see, example 5. Well, here I have multiple ways of executing conditionals, which is one of the two things, major things in programming, is making conditionals, so diverting the execution of the program according with something that you need to test. And loops, it means do some repetitions or something. Right? It's permission denied. So is there? Oh, but it's not executable. Okay. So I can. This is one way of doing it. So it's testing different ways, numbers that in the case of shell, they don't have the idea of numbers itself. When you put a 0, is the character 0, is not the number 0. So this was done not for doing numerical operations, it was more for dealing with files. You can do numerical operations, but more indirectly. So that's the idea. So there are a few examples here of conditionals, loops. I will try to skip that and move into awk and shell script. So here I have a code. This is an MPI code those like that they demonstrate before. This code is computing pi. It's having multiple processes and they all work together with a series that converges to the number pi. So here is the loop here that is compiling pi. So the sum is collecting tiny little pieces that when you combine them, it will have pi. And different processors will compute different portions of the series. Okay. So I am demonstrating here how you compile that. That we already saw this. Module load, parallel, open MPI. To the 16. 16. Should I have it? Oh, maybe the 4. Or 1.5. Okay. Okay, so I compiled this code here. And I will be using this for running a script. I will be the executable, using the executable this for testing how many elements of the series will give me a certain value of pi, at which point I will get 5 digits of precision, 6, 10, whatever. So this is the idea of this code. So I compile the code and I will be trying to run, for example, this with 100 elements in the series. So it will compute pi using 4 processors. So and it tell me that the error, because I have the value of pi with with enough digits to compare. It told me that after like six good ones here, I start having a divergence here. So I start having an error that is this size. Okay. So what I will be doing with the script is for the exercise is to try to use this kind of things to loop across multiple values of the final value that you have here. So try to make a loop where you try just 10 digits or 100 or 1000 on 10,000. So make a script that will run that. An extra will be to submit this script to the cluster. So you don't run this on the head node, you will be running on a compute node. And even better than that, eventually using 2 machines working together on solving that and making a big number of elements in the series to get as precise as possible. You can get to 10 to 10, 10 to minus 10, the error, 10 to minus 12, the error pretty much. Otherwise, you start getting errors because you are using double precision and you have to extend the precision of the machine. So that is pretty much what you can do for this exercise. Is pretty much doing something like this, what the exercise is proposing. But now I would like to move in the final minutes to 2 commands. This to demonstrate those. Probably will try to show you here what they do, and they are very powerful. And it's this one here is shell scripting. So I have an output here. It should have an output here. So this. So this is a real output from a real code. It's big. Many lines. Do you want to see what many lines? You can execute this command, and this, well, not that many, 92,000. Still is something that you will not be reading one by one. But this is still something big. And the problem here is that this is the result of the execution of a code, and it will produce values of things that will be interesting to look at. Kinetic energies of some certain atoms, energies, forces, all those sort of things. And I would like, for example, to capture forces or capture energy to see if the system is reducing its energy or not, or the energy that's supposed to be constant is effectively constant, all those things. So that's what I'm doing here. I'm using this. You will see a little bit of the file. And what I'm doing here, for example, is using grep. Grep is one tool for extracting lines of in a text file that contains a certain character, so time step, for example. I will be just printing those lines that contain this. So this is something I'm doing here. Also, well, you see that in this case, there are different kinds of lines that contains that. There are those that contain time step, and there are those that contains time step in the middle of the string, in the middle of the line. So eventually, we like to take just those that time step is at the very beginning. So there is a way in grep to indicate that, and it's something like this. So I would like to put something that contains time step, and in the worst case scenario, it contains nothing before that, or in the worst case scenario, some spaces, but no more than that. So just spaces. With this, I will be filtering better the output. So just those lines that contain time step at the very beginning, eventually with some tabulator or something like that, it will be captured. And after, I could take, for example, that line and the line after that, and 13 lines after that, and one line before that. So this is what these A and B are doing. So I want like this, and I will like 13 lines, whatever it was, 13 lines after that line, and one line before that. So to get like a scope of what is around. Why? Because I was reading the file and I noticed that before that I got like this line here, it's telling me total energy, like a summary of one time step of this molecular dynamic code, or the so what is going on with that. It will tell me the time step, but also just after that, I have some extra lines that contain useful physical information that I would like to see, to process, to visualize, eventually to make some plots out of it. So that is important to me. So I'm from this long text file, I will be just capturing those lines. So that's pretty much what I'm doing here. And now I would like to just make a pipe, is this vertical line here, and just extracting those lines that contain E tot, which is the total energy in this, for this package, for this code. So it's the same here, but now after it's scrapping all that, I would like to just take one line, this line, that contains the total energy. Why? Because I need to check that if I am doing this correctly and the energy is preserved in the system, I should be observing no changes in the energy, no matter the number of iterations I execute this. So energy should be preserved to a certain error or a certain degree. And finally, I would like to, for example, get an average. What is the average energy that I'm getting? So the energy in this kind of simulations is oscillating. It's a little bit, it's pretty much constant, but it's oscillating a little bit. So I would like to make an average. So there is another software that is called OC that allow me to do that. And I will go a little bit deeper in the last 3 minutes that I have here to show you a little bit how OC is. Otherwise, you can see it. And we see, yeah. So I'm executing awk here. So I am doing exactly the same up to here. So this one, the previous line. And now I am adding this section here. So I am piping. This is a pipe. So the output of one of the previous execution will be the input from the next command. And the next command is called awk. And here I am taking the sum of the third element on each line. So this is the first, like the third column. So these columns or words are whatever is separated by the space or something that looks like a space. So E dot is the first column. Those equal signs are the second column. And this number here, it will be the third column. So this is what I'm capturing here. $3 means the third column. And now I am taking like a counter how many lines I got with this number, how many, and I will keep in that like in my pocket. And at the end, when I finish processing all that, so and the variable start with 0. So by default, when you put the variable at the very beginning, it start with 0. You don't have to initialize it. There are ways you can initialize something if you are doing instead of the sum, you need like a geometric average. So in that case, it's 1. So there are ways to initialize that, but in this case, I don't have to. I am just taking a arithmetic average. So I take this, and at the very end, if I got more than one case, so the file effectively was computing an average, I just print the sum divided by the n, and I will get here, which is effectively the average of all those numbers. Otherwise, what you are doing, if you don't know arc, is copying and paste that into an Excel file, which is a pain, but I think is still doable, at least for this. But if it contains hundreds of thousands, you will not be able easily to scroll all that, paste in an Excel file, and put in the box a formula for the average of that column. Well, that's one way if you don't know that. Another way is to store that in a file, and at that moment, maybe you can do a Python script, will read the third column and compute the average. And I assure you that if you do this for something with many thousands of lines, whatever you do with Python, most likely is slower compared with what you can do with this very simple. Well, simple when you know, but you have to put it there. But once you know it, it's relatively simple to type to compute the average. It's like that. So there are more things that now I'm running out of time, but let's say they have like extra exercises that are basically more elaborated on the theme. They follow the same idea. I have this one. In this case, I have like, I think it's 4 million lines. So several files, actually several files here. And all those contain pretty much that, some lines that I'm capturing. And with those files, just from one file that contains millions of lines, I am capturing a certain data, which is here, the total energy, something. I basically following step by step for you to demonstrate what I'm capturing there. And at the very end, I am using awk scripts, more elaborated with initialization of values, all that, to get the minimum, the maximum, the average of the total energies on the energy per particle, things like that. And if I'm not wrong, I don't have, or yes, they have 7 million lines total in all those files. And rest assured, in some cases, for simulations, molecular dynamics, this is not that big. So you end up with really big files, and you need to process those. They contain energy, they contain values, they contain physical values that you need to process. And if you try, I think that I don't know if I have the Python script, one simple Python script, and the Python script was 100 times, and it was not that bad. It was 100 times slower compared with the awk script. So that is the final message here, that these two commands, grep and awk, exist, and using them will do relatively simple stuff very, very efficiently. And with this, I will be wrapping this workshop, Introduction to HPC. Thank you very much for all of you who follow me in these 4 sessions. We end up with 9 participants, which is okay, not that bad. So I hope this help you somehow in your research, in your on whatever you are doing after you graduate to this. You will be working with other teams, companies, institutions, and they will be facing things like this, where you have to automatize things, where you have to work with other people, and having version controls, doing some scripting. Otherwise, you will be too very, very, very light in the night doing something that you can do in 10 seconds. So all this will serve you well at some point in your life. So thank you very much, and see you tomorrow for the